Okay, good morning everybody. I hope everyone's having a wonderful day. So just a couple of quick things just to mention is as I put out a message yesterday about it, I put out the exam format, so just give that a read. If you have any questions or concerns, feel free to ask me about it. And another thing is, remember your final assignment is due by the end of December the 5th, so the 8:30 rule is in effect. It's course for that as well. So just keep these two things in mind. Do keep in mind that the exam is creeping up. It's on a Saturday. That's something I didn't have any choice in. That was just scheduled by the university. But most certainly that's just a few things you should keep in mind. So anyways, I want us to get back to where we were last day, where I kind of had to stop because we were going a little longer, and I apologize again for that. But I want to come back to the 0-1 Knapsack dynamic programming algorithm. So remember I was doing this example the other day where I had 5 items and I was filling in this table row by row. And then for each row, I evaluated the columns. And there were 2 interesting positions when we were filling in this table. It was namely, for example, if I were to consider, let's say if I pick, say, this one right here. Say item number 4. So this would correspond, so remember, the rows represent my inclusion of the next item. So in the proof, it doesn't matter which order these items are in, which is great. But in our table, we're going to consider the items as we include 1, then 2, then 3, then 4, then 5. And that's 1, 2, 3, 4, 5 here. And the columns are going to represent a knapsack capacity limit. And that'll tell you, okay, so any one of these spots will tell you the profit, in this case, optimal profit, for a knapsack that includes that many items with that knapsack capacity. So for example, here, if I look at this one here, this is, if I consider the first 4 items with a knapsack capacity of 5, this is actually what the optimal profit would be. So the way I computed this is for example, here, when I look at my items over there, notice that the weight so if I look at item 4's weight, it is 2. So there's kind of 2 positions really to look. The one directly above it, which is meaning I don't include item 4. And I look at what the best thing is currently. Or I look at a position where simply I see, okay, well, what's the weight? So that would be 2. So you check and compare it against what's currently sitting here, which is a 5, versus if I looked at without the item. So that would be the 2 off the weight. So you take the capacity minus the weight by 2. So 5 minus 2 is 3. So you sit right here and you ask, okay, well, what's the profit of item 4? That is, profit is 4. So we have 4 versus 5. We put the 5 here because that's the larger of the 2 values. So when you're building this table, you really just have to look at 2 positions for each one of your cases here. You look for the one directly above it, then you go to the position where you take the knapsack capacity minus the weight of that item, and then you just add on the profit for your item. Because remember, that's where you're going to consider where you're going to put an item into the knapsack. So you really have these 2 possibilities. Yes? Yes, that's a very good point. Yeah, so the first thing I should point out is that the first row and the first column will always have zeros in it, because that's how we define the recurrence. So when you're actually writing out the dynamic programming algorithm, when you're tabulating this, you'll actually end up with 2 loops that are just going to literally fill in the row and column. The first row and the first column with zeros. But yeah, the reason why these all looks like a triangle like this is indeed the case, that you'll notice that, yeah, the weights of these, they start off from largest to smallest in this case. So nothing really interesting happens until later on. But yeah, you're indeed correct that the items, the ordering of these weights does actually play a very important role for how this table might look. That's actually a really good observation. But yeah, exactly. No, see, you're getting this. It's really good. But remember that this entry right here, the bottom right corner entry right here, this is the optimal profit over all of the items with knapsack capacity that's the one that's desired, in this case 10. So just as a reminder, the way I computed this is I look at the entry above it and I say, okay, so I have 11 versus, okay, well, let's wait a 5, that's 2, right? So I look in this entry and I ask, okay, I have 11 versus 10 plus the profit of item 5, which would be 6, so that's 16. So 16 versus 11, I put the 16 here. So when you're filling in this table, it's generally, you just got to get yourself into the habit of doing this. You'll see that when you're doing this on the assignment, it'll very much feel natural after you do this maybe about 5 or 6 times when you're filling in the table. Just make sure you're kind of cozy applying the recurrence. If you're really just not cozy with the idea of the recurrence, just go to the notes, look at the pseudocode like I have over here, and just try it out for yourself that way. But sometimes I know with some students, when you look at things recursively, it isn't quite as clear sometimes until you see it as like literally written as loops. Because that's how we would typically do it bottom up with dynamic programming. So are we okay with this up to this point? I just want to get us all up to speed where we were. Because I got to tell you how you pick the items using this table. J minus Wi. Yeah, so just to elaborate on what I have here. So remember, we have there's 2 real things that happen, right? We have to look at those 2 positions. The one directly above us, which is val I minus 1j. So that's the entry just directly above us. The one that is to the left, where I subtract off the weight, this would be in the row directly above it. And then this would be the column that is to the left if I subtract off the weight of item I. So remember, this case right here, where I have this right here, that is me just simply adding in the item I. That's one thing I really want you to take note of, because that's going to be really relevant when we start talking about how we pick the items. Yeah, no worries, no worries. One thing to keep in mind when you look at this pseudocode is that the profits and weights are 1 indexed. They're not 0 indexed. If you were to actually have it where it's 0 indexed, it would indeed be Wi minus 1, where you just take off 1. So that's just one of those small little details for us. But I mentioned that last day, that we're indexing the profits and weights by 1 through n, and our tables being 0 indexed, starting at 0 up to whatever the value is, minus 1. Okay, so let's proceed then. So let's go this way. I'm gonna walk myself on over this way. I just gotta walk my way over here. Just a casual Monday, okay? So I need to talk about this backtracing process. So this is actually a rather common aspect of dynamic programming when you're tabulating the table. And I must stress that when you're actually looking at this backtracing process, one thing you also have to keep in mind is that it's heavily dependent on the recurrence relation. So when I formulate that relationship that the optimal has with those sub-instances, that will tell me very quickly, and keep in mind it's something very crafty when you're tabulating this sometimes, that what we're going to do is we're going to start actually way down here in this bottom right corner, and what we're going to do is we're going to pick the items based on what the entries in this table look like. So we're going to use this table, and based on how we computed each value, we actually tell based on what the table looks like, believe it or not. We can do this what we call often a backtrace. Sometimes people call it backtracing. Some people call it the process of constructing the solution. I like to call it backtracing because it's like you're tracing back through all your decisions. So we start off in that bottom right corner, and it's based on the recurrence. Now, as I mentioned a moment ago, so we're going to start off over here. So we start with I being n and j being w. So I is going to be the row, j is going to be the column. And we're going to start right here. And what we're going to do is we're going to simply ask, we have 2 cases. So if we look back at our recurrence, I told you the idea was that if I look in the entry directly above, say for example right here where I have 16 versus 11, if I see that they're not equal to one another, that means something, right? Remember when I filled in this table, whenever I looked at one of these entries, I had two possibilities. Either I take the one directly above it, or I find a better one by looking along another column that's in the row directly above it, right? So when I do take this one that's directly above the entry, in this case I didn't, what would that say? That would say, of course, that I didn't put the item in the knapsack, right? Because I just considered the first I-1 items up to that point, rather than including item I just take those first item one. I take the best answer from the I-1 items. Now, I don't know if those I-1 items are taken or not. That's going to be what this backtracing process is going to help me do. But here's the first thing. Remember, when we put an item I in, what we did was we included the entry, that's the one directly above it, and I shifted all the way towards another column based on the weight of that item when I take it away from the knapsack capacity, which would be represented by that limit on the column. So when I know that happens, which means that these two values are in fact equal to one another, then we include item I, and then all we do is we literally just look back at a recurrence. What did the recurrence do? So remember, I take the larger of two values. I take the one that's the above it, or the one that is, say in our case, I believe it's 2 off here, or I take this one. So if I take the item, this corresponds to me picking out item I. So I've considered item I, this would be this row here, and then I move myself up one row, and then I shift over the columns that would be the weight of that item. So this is actually very similar to how I talked about the principle of optimality in my proof the other day, where if I take an item and I remove it from my optimal answer, I could tell you that the sub-instance is optimal, right? Well, you can reverse this process, right? So if I imagine I start off with, say, some optimal, I can always put back in the item, and then I cause the instance to now have less. I filled up more of the knapsack, right? But I can reverse this, right? I could take away the weight from that item. So we're going to unwind all of these decisions to tell me what the optimal knapsack looks like. So when we do this, that's all we're going to do is whenever this happens, we're just going to go up one row, and then we're going to shift along the columns towards the entry that would be the one where I decrement off the weight of that item, because I took that decision when I put that number in there. So for example here, I can clearly see that the row directly above it for 16 is 11. You know that you've taken, say for example, item 5. So otherwise, if we see that they're in fact equal to one another, that means I know right away that the item hasn't been taken. So we just go up one row, we don't consider that item any further. And we just keep doing this until we either reach the first row, which would be the ones with all the zeros, or the first column. So we just walk ourselves back through this process. You just keep repeatedly doing this. So I have some pseudocode in the notes if you aren't convinced or don't really get exactly this process. We're going to be walking through an example of doing this. So first, is this clear for everybody? Just so, remember, all I have is those two cases. Either it's going to be that the entry directly above my entry I'm currently considering equals or doesn't equal my value in my entry that I'm looking at right now. And I start in the bottom right corner and I work my way, and you're going to see that I'm going to kind of work up, left. I'm going to work my way through the table. I'm going to be unwinding all those decisions based on what I put in that table. This is one of the neater aspects of dynamic programming. So if you walk out of this class with anything about dynamic programming, it's this cool process you could do with it. So if you aren't just satisfied with the value of the optimal profit, this is how you can actually do this with R0 and knapsack algorithm. Okay, so if we're okay with this, I'm going to proceed back to the board over here, and let's walk through this process, okay? So let's go all the way back over here. Okay. So to make this a little easier for everybody to see, I'm going to, actually, let me use a different color marker just to make this a little easier for us to see. So I'm going to use red. Hopefully this red marker is okay. So I already told you at the beginning. So remember, I start right here. This is where I start. I look at the entry directly above it and I say, okay, these don't match. So I know right away I'm going to include item 5 in my knapsack. So what am I going to do? I decrement I by 1. So I decrement I by 1. Now keep in mind, it doesn't matter if you decrement I by 1 or you decrement the j first. In the pseudocode, it makes no difference. But I like to just think about it like you're going up like this, and then we're going to go left. We go left by how much? Can somebody tell me how much am I going to go left from this spot? 2. Yeah, exactly. 2. So I'm just going to go, I'll just go this way. And now I'm right here. So now I'm considering this 10 right here. So I look at 10 and I look at the entry just directly above it. So I got, 10 and I have 6. They're not equal to one another. So we know right away that item 4, that's going to be in our knapsack. So what am I going to do? I'm going to, let's see. So what's the weight of that? Well, it's also 2, right? So you know right away, okay, I'm going to decrement I by 1. Then I'm going to decrement j by 2 because the weight of item 4 was 2. And now look at this. Now this is where it gets interesting. Okay. So now notice that this 6 is in fact equal to that 6, right? So do I take item 3? No, right? Very good. Very good. Very good, everybody. So we're not going to consider that. We're going to go up. Okay. So now 6 is equal to 6, right? Do I take item 2? No, right? Very good. Very good. Okay. Do I take item 1 though? Notice it's 6 versus 0. Yes, so now we take item 1. And then notice that I decrement I by 1, and then I subtract off the weight of that item, which in this case is 6. And you'll notice I'm going to be sitting right in either the first row or the first column, and we're done. So believe it or not, you can actually achieve this with just simply using a while loop. So what are the items we're going to take? Let's summarize that. So the items I've taken are 5, 4, and 1. And of course, it's profit. So if you're wondering about its profit, so it's the optimal profit, of course, we knew already from last day. So the optimal profit was 16. You can always check this fact by just simply summing up over these. So notice that I have 6 plus 4 is 10 plus 6, that's 16. And that's all it is to the backtracing process. So you'll very often, like I said, you'll find that this backtracing process always depends on the recurrence relation that you use to derive the dynamic programming algorithm. So when we get to when you get to reading about the longest common subsequence, you'll see that the recurrence there, it's a little different than the one I have here for the dynamic programming, but you'll see that the backtracing process, it uses the very same idea. It's just either I'm going to have a match in that case or not have a match, and you just take like the better of the two answers. Then that will depend on if you go left or up or diagonal. It's a pretty interesting example, but are there any questions about the backtracing process here? If I asked you to do this on the exam, would you be comfortable doing it? Because I'll tell you a heads up that you're going to be asked to do this on the exam. So But yeah, so hopefully the assignment will give you some practice to try this out. But yeah, it's in the exam format. It tells you right there. But yeah, so anyways, I want to talk about the time complexity of the zero and knapsack dynamic programming algorithm I gave you. So don't worry too much about the details of what's going on inside of here at this stage, because it's all based on the recurrence relation I showed you the other day. But if you were to analyze this out, you'd notice, okay, so I have a for loop here. So this is going to be big theta w many operations. The second loop, this is big theta of n operations. And then I have a nested loop. Like this, that's the one thing that you'll notice very often with dynamic programming algorithms is the analysis tends to be pretty simple because it's just based on how you build the table. Oh yeah, one small step I should also include up here. There is a step that's above here where I create the array, right? I have to create the 2D array. And its dimensions are n plus 1 rows by w plus 1 columns. So when I create this, this is one other important aspect of this, is this part right here, because remember I have to allocate the space for this. This is going to take big theta n w, because each time I allocate some memory, that's going to take some time too. So when I do this, yes. Okay. So I should also specify that it also will allocate them all to 0. My apologies. Okay, so let me elaborate. So first, in the model that I gave you at the beginning of the course, we also counted if I allocate space, that also actually attributes to the time complexity. So if I allocate, let's say, one memory cell of space, that takes me one step to allocate that. So if I allocate n times w space, that will take nw time. So that's regardless if there's zeros or not. So I'm mostly including these loops here just for as a matter of good practice, because you don't know what's going to be sitting in that memory. It might be the case that they might have a bunch of garbage in them. But so I'm just making sure that they're set to 0. But in a lot of languages, you'll just be set to 0 when you create the array. But not every language is like that. But hopefully that clarifies that. But yeah, so we have this step, and then we have this nested loop. Everything that's happening in this nested loop is some constant number of operations. So this is going to all be constant number of operations. And then I have my nested loop. This is really easy to analyze. This is something I could have given you in a previous class. So notice that I have n and I have w here. So you know that this is going to be, it happens n times and w times. So I have that combined. So you know this is going to be, since that's constant number of operations, you know this is big theta n w. And we know the time complexity then. Time complexity, as said in the chat, is big theta n w. Note that returning here, if we had to be very nitpicky about this, that takes indeed a constant number of operations. So if you were to sum up, you take big theta w plus big theta n plus big theta n w plus big theta 1, you should get big theta n w. Many operations. Now, I have an interesting question for you. So up to this point, I've always talked about how there's different complexity classes, where I say like, okay, an algorithm runs in linear time, and then we may be interested in the problems that can be solved in linear time, or those that are interested in where we could solve them in quadratic time. I have an interesting question for you. Is this running time polynomial with respect to the input size? I will tell you it's an interesting question in this case. But what does everybody think? I like to show this one to students because it gives you something that's a little bit different. So just remember back to the beginning of the course when I talked about input size. Remember, input size is the number of bits I need to represent the problem instance. In this case, I have a knapsack capacity. This is an integer. I have 2 arrays with n entries in them. Each of those are going to be encoded with some number of bits, but for our purposes, since they don't appear all in the running time, we're going to have n times some, with respect to us, there's just some constant number of bits for each one. Think of them like 32-bit integers or something. You can also think of this w also in the same way. But there's something very interesting about this, if you think about it. So n, that's okay, right? That looks like something that would look like a polynomial if I asked you if this ran in polynomial time. But what about w? This w is a little bit strange. Does anybody have any suspicions of why the w is a bit strange here? So notice that w is not a constant. It's actually a part of the input too, right? So notice that this w right here, that's an integer, right? But how many bits do you use, say big O speaking in terms of big O, how many bits do you use to represent w? This is going to be one of those examples I pointed out near the beginning of the course, and I told you we're not going to really run into it except for some point later on in the course. This is that time. This is one of those stranger examples. So I'll let you think about that. I'm going to move on over this way, and I'm going to talk a little bit about this. Then once we're done talking about that, I'll talk a bit about backtracking. And that should be the rest of today. So let's, so the time complexity, remember, is big theta n w. So it seems efficient on the surface, right? So it seems efficient on the surface. Now, in the context of dynamic programming, which is a hard problem, this is a rather good algorithm. A lot of people will point you to this algorithm and say, this is one of the best known algorithms we have for this problem. Believe it or not. So here's the thing. The n and the w, they both look like polynomial terms, right? They seem that way. So all the terms of the running time, in the most literal sense, they are polynomial, right? But that's not the only part of when we talk about the efficiency of an algorithm. We measure it with respect to what? The input size, right? So we have a very special name for algorithms that have time complexities where if you read them, they look like a polynomial, but they're actually not polynomial with respect to the input size. These are what we call pseudopolynomial time algorithms. So there's a special name for these. There's a lot of interesting theory around optimization around these types of algorithms, and they often closely relate to dynamic programming, believe it or not. So these are often what we call pseudo-polynomials. So if I ask you what a pseudo-polynomial is, so this would be what we call pseudo-polynomial time. I'll give you a more exact definition in a moment. It looks like a polynomial, but it's actually not polynomial with respect to the input size. In this case, think about it. The input size of w is not constant. I must stress that if you know w is a constant, this is indeed going to run in polynomial time. So that's one thing you can also keep in mind. If you know the knapsack capacity is never going to change at all, then this will be a polynomial time algorithm with respect to the input size. But remember, W is a part of the input. It's actually something that also, remember, every problem instance is formulated with those parameters. This includes the knapsack capacity. In this case, the input size of W is not constant. It is represented with K equals big O of log base 2 of W bits. And I must stress that the W could be considerably larger than the items. So if you want to be very nitpicky about this and say, okay, well, each one of your items in the arrays also are represented by bits. But remember, W could be much bigger than all of the values in those arrays. So the reason why this matters in this case is because this is an optimization problem that uses numbers in it. And notice that W is not just, it's not an array with a number of items, it's a number. It's just a number flat out. So when we look and see it there, what's W with respect to log base 2 of W? So if I were to ask you from a scale standpoint, if I told you I had something of log base 2 of a something, and then I had a something that is just the something without the logarithm, what's the difference between these two, proportions-wise? There's a reason why we really like logarithmic running times, for example. This is one of the reasons why, but this is, what's the difference between W, like not, I don't mean subtraction, I mean proportionally. If I give you W and log W, what, like, it's the scales, just think about it in terms of magnitudes. So is it like a polynomial, or is it like exponential? Like, what does it look like? Yeah, log W does not increase that much, right? But W can, it grows linearly. But the difference between the proportions of these two is actually exponential. So what do I mean by that? That means if I were to write out this running time, another way I can write it out is by making it n times 2 to the power of k. So, because remember, W is represented by some number of bits, right? And we don't care about what W exactly is, it's just how many bits we use to represent it. So with respect, that says with respect to the input size, the running time is actually exponential. So this is why we call it pseudopolynomials, because it looks like a polynomial, but it's actually something else. And in our case, it's running an exponential time. This is one of the cases you're going to run into this in this course, and I want to make sure you've seen it once. So when you deal with numbers, so optimization problems, typically when you run into them where they encode numbers, sometimes you have to be careful when a number pops up in the running time like this. Okay, so that's really the big takeaway from this, is if you see sometimes a number that is in fact a number that's represented in our problem, you have to be very careful when you're designing the algorithm so that doesn't pop up, because it actually could represent something else in terms of the input size. Why? Because remember, this table, one of its dimensions is W. So if W is, say, 100, the dimension of the table is in fact 100. It's not log base 2 of 100. It's 100 straight up. So just let me define what pseudopolynomial time means. Pseudopolynomial time . So I'll just say its running time its running time is polynomial with respect to the input size, when the numeric part, I will say numeric part of the input is represented in unary. Represented or encoded, whichever term you prefer. Now, if you're not familiar with unary, you know what binary is. For example, you have a system like it's represented with zeros and ones. Unary is just where you have ticks. So like a bunch of ticks of ones, for example. So if you were to take these numbers and say, okay, well, I'm allowed to have it where the input for these numbers is encoded as just ticks. And I say, okay, it's a polynomial. Notice that this W is okay now, because now it represents literally a number of ticks that I'm encoding for my input instead for the numbers. But this is actually, believe it or not, you might say, Dan, well, that seems kind of unreasonable, right? Because now your ticks are allowed to be exponentially long, right? That's what's wrong with the fact that we can use an encoding like unary. So some people will define pseudopolynomial as well as it runs polynomial with respect to the input size within the context of where you could encode the input in unary like this. So for general theoretic purposes, typically people will say that the main inconsiderate way of encoding the input is unary. So for example, ternary, binary, those will not have any of these issues. Unary does though. So that's why I'm saying unary down there as opposed to some other encoding scheme. So that's all I have to really say about Knapsack, okay? So are there any questions about this? I can elaborate any further. I always have time after class too. But feel free to ask me about this. Just remember, the reason why here is because we have a logarithmic number of bits used to represent W, but the running time, W just straight up appears. What would make this polynomial with respect to the input size if it was actually n times log W, for example. Okay, so if we're okay with that, I want to make one remark. There's another example for dynamic programming I have in the notes. I'm going to ask you to read it. I'm going to ask you to read the section that I included there on the longest common subsequence. So this one, if you're curious about bioinformatics, this is an example of what I would consider one of the more fundamental problems that you might run into in an area like that. So this is a string-based problem, and your job is to figure out the longest sequence where you don't consider about the contiguousness or if the symbols are right beside each other or not. You want to find the longest string where the order matters among two common strings. We call these subsequences, and you want the longest one. So in that case, you'll see that we're going to have a nice dynamic programming algorithm there. That algorithm does not have the same issue as this one does. But this one actually has some very interesting theoretic properties. For example, you can always recast this dynamic programming algorithm where one of the dimensions actually is the total profit as opposed to the knapsack capacity. So you can actually enumerate over the optimal profit, which obviously it's not a part of the input, right? That has a very similar problem. It's also pseudopolynomial. But you can do some neat things with it. If this was a course that had also some other things, I would talk more about that. But let's just say that there's some neat things you can do. For example, you can approximate how good the answers are using a dynamic programming algorithm like that. But that's just a side note. That's not anything I'll ask you about. But anyways, that being said, I'm going to spend the remainder of class talking about brute force and backtracking. So I'm going to give you an introduction to this because we're starting to kind of wind down for the course. But I want to give you just a general idea about what kind of tools do we have if, say, we're running into these problems, like Knapsack here, for example. This is not, in the sense that I'm going to talk about later on this week, it's not an easy problem in the sense that the best known exact algorithms we have for them, believe it or not, run in exponential time, just like my dynamic programming algorithm. So I want to make sure I show you one trick that you can do to try to improve or design algorithms based on stages of making decisions. Quite similar to how I did in Knapsack. Quite similar to how I did in the greedy algorithms, where I have a sequence of decisions where I create a partial solution that builds me to some feasible solution. So we're going to talk a little bit about brute force. And just a little intro on backtracking. So if we need a little bit more time next day, I'll definitely use it. So when you're solving harder problems, we often want to compute one, the best, or possibly exhaust all possible solutions. Just a few examples of what I mean by each, because backtracking can be adapted to compute just one solution. It could be for computing the best answer, say if we're talking about an optimization problem, or it could be used to exhaust all possible solutions, because there maybe exist many of them. So I'll just give you a few examples of what I mean by this. So suppose I want to have one solution. So we did something like this in class, one solution. Suppose we want to find a path from the start to the end of a maze. So in this case, we just need to find some path, right? That's all we really need to do. We may want to find an optimal knapsack, just like in our problem we had before. So this is an example of a best solution. Another example for the last one here is very often we may want to actually construct a whole set of objects that are all technically solutions by how we define them. So a good example of this would be a list of all permutations of objects. So this is exhaust all possible solutions. So just to give you a flavor for what kind of things you can use these approaches for. Now, you might ask, okay, well, what's kind of the formulation that I'm going to use very often? So we assume an algorithm constructs a solution x1, x2, all the way up to xn in stages, akin to what I've been talking about previously where we build a partial solution. That's literally what I mean here. In stages. So this would be a sequence of objects. Sequence of objects are chosen from a specified set where it may have to satisfy some criterion. Now this is not to be, so this is just meaning me saying that it has to follow some constraints, some criterion. And I'm also going to define a partial solution like this. A partial solution x1, x2 until I get to xi. for I is less than n. So I'm going to have a solution that I'm going to want to get with n objects. And then I'm going to have every single step, I'm going to have a partial solution. So I'm going to do this in stages where I'm going to start off with no choices for objects. Then I have 1, then 2, then 3, then 4. When I'm doing this process, I want to make sure that every single time I make a choice, I'm still working with something that follows the constraints of the problem. Just like when I talked earlier on in the course about greedy algorithms, when every time I make a selection, I want to make sure it stays a feasible solution with respect to what I've considered so far. I want the same idea here, but it's not nearly as constrained as a greedy algorithm would be. This is really very much where we're just going to try everything. So you're going to first see that I'm going to be very lax about this last part here. You'll see when we get the backtracking itself that I'm going to then try to impose this. So the big thing I want you to be aware of is that there may be exponentially many potential solutions. So just as an example, our knapsack problem, every one of our instances, if I give you n items, there's a potential that there could be 2 to the power of n possible choices at least, in terms of big theta, of possible knapsacks, right? Because I can make n possible choices with n items. Either I put them in the knapsack or I don't put them in the knapsack. You're going to find in our example, when I do it next day, what I mean by this. Now, I'm just going to briefly define what brute force is, then we're going to wrap things up here, okay, everybody? Then we'll play more about with brute force and backtracking next day. So let me just quickly just note down what I mean by brute force. Okay. So one way to solve problems like this is by using brute force. And some people will call this exhaustive search. If you're curious, some people use this phrase. At least in the context I'm going to present it to you. So the first option is very natural. Try all possibilities, okay? So when we come back next time, we'll see what I mean by try all possibilities. And take the solution, or potentially many solutions, as required. So I mean, I'm gonna just straight up be like, yeah, we're gonna just try everything. You're gonna see how I'm going to formulate this next time. And when we come back, we'll see an example of this and see how we can improve it using this concept called backtracking. Okay, everybody? So when we come back next time, we'll talk more about that. So I'll say thank you very much and have yourself a beautiful day. I'll see you later.